So yes, I'll be talking to you about the approach to scaling CouchDB with BigCouch that we've developed at Cloudant. And I'll begin with a very brief one-slide introduction to CouchDB. I assume most of you in this audience are pretty familiar with it at this point. A little bit about BigCouch from a high level, from a practical perspective, how you go about getting the code and running it, and more details about how the clustering actually works, both from the level of the client application and from an internals perspective, for those of you who might be Erlang hackers out there. Okay. So me, my name is Adam Kocoloski. I am one of the founders and Chief Technical Officer at Cloudant. I've been hacking on CouchDB for a couple of years now. Knew that I wanted to build a system that looked a lot like what CouchDB wanted to be, and so I decided to get on board with that in the middle of 2008. And at the time, I was a graduate student studying particle physics, and we do a lot of needle and haystack kinds of big data searches in particle physics. And while we've developed some pretty cool systems to let us do that sort of thing, some of the frustrations that I had, as a graduate student, just keeping track of bookkeeping and worrying about changes in data formats and that sort of thing, was a source of frustration for me and a motivator to help, to tell me to build something better. And this is part of our attempt to do that. So BigCouch is something that has been in development basically as long as I've been working with CouchDB. It's something that I've always, thought was an important part of the future for this project. And it's it's an open core model. It's a core piece of the software that we run at my company, Cloudant. You can find me most easily, actually, probably through IRC. I'm always in the CouchDB channel on Freenode and also on the Cloudant Freenode channel. So there we go. One more plug for Cloudant. I'm lucky enough to be able to work with CouchDB on a daily basis and help make it better. And that's because my company provides hosting management and support for CouchDB and, of course, for BigCouch. We offer a variety of hosting plans ranging from self-serve, single sign-up, shared cluster kind of stuff to bigger iron installations for companies who are betting big on CouchDB as a part of their infrastructure. So I promised one slide on CouchDB. Here it is. It's a schema-free document database management system. The documents are JSON objects, and if you need something more flexible than that, you can attach any type of binary data to a document. The database is accessible through HTTP, so your basic CRUD operations map to HTTP verbs, and it's a nice way to interact with a database in today's web services heavy environment. But it's more than just a key value storage. It also has secondary indexes, which we term views. So these are persistent materialized views of the data, and instead of being generated with SQL, they are generated with an incremental MapReduce operation. So there's an embedded JavaScript virtual machine in CouchDB that allows you to write these map and reduce functions in JavaScript. And CouchDB takes care of running those over the data, storing the results in a B-tree index, and incrementally updating them as the state of the database changes. So this is a powerful way to extract information about the documents that you've stored and also to report on them in some aggregate fashions as well. One of the really unique, cool things about CouchDB, though, is the support for replication, which is more than just sort of the log replay stuff that you might get with a relational database. It's really built-in deep support for multi-master disconnected replication topologies. So at the core of the database, CouchDB is using this multi-version concurrency control model for each document. So there can be any number of versions of that document where different editors have changed it in some fashion. And the database is able to keep track of all of those versions that are being created. And the replication takes care that if you replicate with all of your different servers, that everybody will agree on what the state of the document is at a particular point in time. So this is particularly valuable in the case of things like edge devices, which may not be on the internet at all times. So they can keep this database locally so that they can access the data when they're not connected, and then even make changes to it, and it synchronizes back up into the cloud when they are connected again. And of course, there's Futon, which is what many people first see when they come to CouchDB. It's a built-in web interface, administration interface for the database that is served by the database itself. And so it's a nice use of the built-in, web server that does all of the other work for CouchDB. But why BigCouch? So what I've talked to you about is awesome, right? CouchDB is great, and it serves the needs of so many organizations, big, small, and everything in between. But in my opinion, at least, the CouchDB as it exists right now is still, a little incomplete, right? It was initially envisioned as, something that could really scale across clusters of commodity servers, and not just scale in terms of, scaling reads by replication, but really distribute the data and operate as a truly clustered database. So in fact, the name itself, at one point stood for a cluster of untrusted commodity hardware. So, it's taken some knocks because amongst all of the NoSQL databases, many of them do have, built-in ways to distribute portions of a database amongst different servers and collect and collate that information at a later time. You see, people like Jonathan Ellis saying CouchDB is not a distributed database. And of course, for some notion of distributed, it absolutely is. You can replicate all over the place. But what you can't do is scale the writes very easily in that sort of setup. Or, in a more pithy way, right? Without the clustering, it's just CouchDB. So we think BigCouch is an important part of the future for CouchDB. Right, so I started talking about scaling, but let's just, step back and say what it is that we mean by that. Right? And what we're really talking about here is not the, vertical scaling, which is a perfectly acceptable way of doing things at a certain level, which just means getting bigger and bigger racks of hardware to handle the database as you just take one server out and replace it with a beefier one and move along with your life. But what we're talking about here is often termed horizontal scalability. So adding, instead of bigger servers, more servers, creating more capacity for writes and for reads. So one of the goals of what we're doing, and many other products, is that the scaling should be transparent to the application, so that when you add more capacity, you don't have to fundamentally change the way you've designed your application. And a corollary to that is that we're trying to design systems that don't have a single point of failure. Especially as you get more and more servers involved, the probability of any single server failing in that cluster grows quite rapidly. And so if you have a system in which certain machines are special in some way, whether they hold information about the mapping of database shards and nobody else knows that, or whether they are coordinators in some other aspect of the operation of the distributed database, you have to harden those machines and ensure that they don't go down. But if you design a system that, as far as possible, doesn't have those single points of failure, you'll find yourself in an easier operational mode. My colleague likes to joke that systems which don't obey these properties can sometimes be termed pseudo-scalars, which goes back to my days as a physicist. Right. So BigCouch. BigCouch, as I said, was built to address many of these concerns that I just talked about on the previous page. So we built it as a system in which you could easily add new nodes to the system, and your computing power, whether that was for writes or for views or anything, would scale with that number of servers. The goal here, the ultimate goal, is roughly linear scalability in the metrics that you care about. We designed it so that any node in a BigCouch cluster can handle any request. This is fairly straightforward. Any of them is capable of calculating where documents are stored or doing any of the logic associated with merging views and that sort of thing. And provided that you've stored multiple copies of your data, provided you've taken advantage of the redundancy options in the BigCouch database, individual nodes can come and go. If you need to take one down for maintenance, or if one goes down without, your permission, that's not a critical problem. The cluster can recover from a situation like that and resolve the inconsistencies that might arise when the node eventually does come back up. And all of this, for the most part, takes place pretty much behind the curtain. As much as possible, we've tried to make a BigCouch cluster look just like a single server instance of CouchDB. And that's really, in part, a testament to the initial design of CouchDB, which always sort of had this thing in mind. features that would be tough to implement in a BigCouch cluster were even removed in the early days of CouchDB's development. So clearly, it's something that's been in the design for a long time, and we've tried to take advantage of that interface as much as possible. So this is a brief attempt at sort of a representation of what the cluster looks like, in terms of the way the database is distributed, and I'll go into a little more detail of it in the next few slides. But for those of you who keep up with some of the various clustering technologies out there, the principles that are outlined in Amazon's Dynamo paper are broadly applicable to BigCouch clusters. And I'll discuss more about what I mean like that in a little bit. But if you're already familiar with the paper, then you'll start, most of this will start to look familiar. It takes advantage of consistent hashing when deciding where to place documents. It's a very simple technique, and it results in an even distribution of data across database shards and a mitigation of hotspots that might otherwise occur if you were updating similar documents very frequently, for instance. The whole thing is built using distributed Erlang. So many of you probably know that CouchDB is written in Erlang, all the way down to the storage engine itself is talking at a very low level in C, but most of it is written in Erlang. And BigCouch itself is taking advantage of the sort of almost seamless distribution offered by the Erlang virtual machine. In Erlang, if you want to communicate with another lightweight process that's running in your virtual machine, you send it a message, and the syntax looks like a particular way. If you're now in a distributed Erlang virtual machine and you want to send a message to a process that lives on another node, you use precisely the same syntax that you were using before. Now, of course, there are physical realities here. The process is now living on another machine, and terms have to be serialized and sent out over some TCP connection. But as much as possible, Erlang makes it easy to take an application that was written on a single virtual machine and to distribute sensible parts of that workload across a cluster of machines connected on a local area network. And so we take advantage of that feature. And so what you're seeing in the graphic here is just simply, I'm putting in a document named law into my database, right? And so when I have multiple machines, I probably got a load balancer out in front that is, round robining traffic to the different database nodes. And so it picks a node, node 1 here, and node 1, because it's, it's smart, it knows the hash function that was used to distribute the data, says, well, I know that blah belongs on partition E, right? And it, furthermore, it knows that partition E is being hosted by nodes 2, 3, and 4. And so it sends out requests to, save that document on those nodes. And, we'll go through the steps that are required in order to give the client the right response about that operation in a couple of slides. But before we do, we'll talk about just, where you get the code and what you do to get this thing up and running. So, right, if you have a shopping list, you need 3 computers to do this right. And the dependencies for BigCouch are really just the same dependencies that you have for CouchDB. You need, ICU for Unicode collation. You need SpiderMonkey to run your views, and you need Erlang. Those are the basics. You can get the code from us on GitHub and do the usual configure, make, install, dance. And when you start BigCouch on these 3 machines, you have to let them know about each other some way, right? And so the way that we've elected to do this cluster management is by utilizing a CouchDB database. So pick one of your machines and tell it about the other 2 by placing these documents in its nodes database. So you see I'm putting into foo.example.com, BigCouch at bar and BigCouch at SAS, right? So I put those documents in foo, and now all 3 of those machines are going to agree that they've formed a BigCouch database cluster. Just making sure they agree on the magic cookie. This is important. Erlang's security mechanism is that there has to be, a secret that was shared in an out-of-band fashion. Otherwise, the nodes won't be able to connect to one another. There's a default cookie that ships in BigCouch, but unless you want everybody else to be able to figure out how to connect to your machine, you can change that. And just making sure that that they all agree on the same cookie is an important prerequisite. And you also have to make sure that you've got the appropriate ports on the firewall opened so that the nodes can actually make a connection to one another. I can answer quickly. I see a question there from David Van Koovering asking whether the cluster database becomes a single point of failure. And the answer is no, because the BigCouch codebase ensures that any change to the cluster database is automatically replicated to all of the other nodes in the cluster. So you can actually change that information on any node, and each of them will get a local copy of it. Right. So now that you've got BigCouch cluster, there are a few things you need to know in order to get the best use out of it. And so there are really 4 parameters that govern a BigCouch database, that govern whether you're going to have a redundant database or simply one that's not. And so those 4 parameters are these Q, N, R, and W. Right? And we'll go into each of them on the next slides. And in each case, we're going to be considering this 5-node cluster. So the first parameter is simply the number of shards over which a database is going to be divided. Right? Some people call these virtual nodes, some people call them partitions, some people call them shards. I tend to use the terms interchangeably. But this is something that at the moment you have to choose at database creation time. So it makes sense to over-provision a little bit because it's easier to move these things around after the fact than it is to split them, although it's something that we're exploring and actively developing. It's certainly possible for more than one shard to live on a node, and as long as you've got the file descriptors to handle it, you can choose values that are quite high. But it makes sense if you've got a database that you anticipate growing quite large. It makes sense to choose a queue that allows for those files, those individual database shard files, to not get too large. So something like 16 or 32 or 64 would be fine. On the other hand, if you've got a database that you anticipate keeping quite small, you may just leave it at a queue of 1. And so this is kind of a nice feature of what we've done in BigCouch, I think, is that people use CouchDB databases for many different things, and they may have many different databases that contribute to the behavior of their application. And those different databases have different needs. And so you can choose when you create the database what kinds of properties make the most sense to you. And so you should choose a queue that makes sense based on the anticipated size of that database. So the next parameter, again, one that you can choose at database creation time, is the number of copies that you expect, the number of replicas of a document that you expect to be stored. And this is simply, n. So what ends up happening here is that when the database is, when the database is divided into shards, each of those shards is duplicated n times. And provided that you have enough nodes in the system guarantees that those n copies of a given shard are on n different physical nodes. So, obviously it depends on how you plan to use the database, but if you want to take advantage of the fault tolerance and the ability for the system to serve your data even when nodes come and go, you should choose something that is greater than 1. And it makes it easier for the system to resolve some inconsistencies if you choose an n of 3, let's say, because then there can typically be a winner in terms of I stored 2 out of the 3 copies successfully. 1 copy. The next 2 are ones that have defaults, but can be overridden at the time that you actually make the request for a given document. And so this really has to do with when the database cluster can tell you that it's done what you asked it to do. Okay? And we call this parameter W. And it only makes sense to set it somewhere between 1 and n. You're asking n copies to be stored. And so what W is going to do is allow the database to respond to you, yes, I've stored your document, after W of those attempts come back successfully. Now, every time you put a document into the database, it's going to write all n copies, or at least it's going to attempt to. But this is just a way to kind of balance between low latency, high throughput operations while still ensuring that if you follow a write up with a read for the same document, if you use these quorum parameters appropriately, you'll see the document that you wrote. Because you could design a system where if you just kept writing, and getting a response back when you only had one copy written, you could design a system where, a next read for that document might not see it because it hadn't actually been stored on all of the nodes yet. But again, this is, these are the kind of things that were probably codified around the time that Amazon published this Dynamo paper. But they're certainly as applicable in the BigCouch system as they are in many of other systems. And finally, the fourth parameter is, just analogous to W. It's the read quorum level, right? So again, it has to be between 1 and n. And the interesting thing here is that since CouchDB has this, very nice multi-version concurrency model, it can actually determine if it detects an inconsistency in two different copies of a particular document. It can oftentimes determine which one of those is, an ancestor of the other one. And if it can determine that, one of them is an ancestor and one of them is a descendant, it's going to pick the descendant because it knows that that was an update which maybe only partially succeeded, but it's going to eventually succeed as, the system kind of recovers from whatever caused that thing to partially fail. And it can say, well, yeah, I know what the right answer is going to be. And so I'm going to tell the client what that answer is. And at the same time, I'm going to trigger a job that starts that repair and ensures that the right version is saved on all of the different, copies. So this is a fairly nice, nice feature. But of course, it presumes that you're using an R greater than 1. Right? If you're using R, a read quorum of 1, you're just taking whatever comes back the fastest. And so that is all well and good, right? But so far, I've just been talking to you about single document operations. And, like I said, CouchDB is more than that. CouchDB also allows you to build secondary indexes using MapReduce. And there's a number of different ways that you could tackle this problem. What we chose to do, I think, is something that is simple and robust. And so each of the database shards builds any view index. You put a design document in, and all of the database shards know about that design document, and they take care to build a view associated with the documents that they're hosting. Right? So locally on each node for each database shard, you have a view index associated with that database shard. That means that the extra work needs to be done at query time. Right? If I do a query for the first 100 rows of a view, I have to ask all the database shards, give me your first 100 rows. And then, not I, but BigCouch has to do a merge sort on the node that was handling the HTTP request to pick the first 100 rows, from the clustered database, right? And so it tries to do this in a very latency-sensitive fashion. Each of the views are streamed row by row from the database shards to the process, that's living on node 5 in this slide, which was handling the user's HTTP request. And node 5 is computing as quickly as possible what the globally first row is, and as soon as it knows what that row is, it sends the row back out to the client. And similarly, if you've got a reduce function, there's an extra step that has to run here, right? So each of the database shards is computing the map functions and also the reduce functions for their piece of the data, right? And if you've written complex reduce functions for CouchDB in the past, you know that there's this step, there's this re-reduce step, where instead of reducing key value pairs from a map function, you're reducing, previously reduced values. And your reduce function has to know that that will occur, right? And so in a BigCouch database, it always occurs because you've got the different reductions on the different nodes, and those are only merged at query time. So that takes care of the way that we do views. And the changes feed, which is such a cool feature of CouchDB, allowing you to be notified about updates to the database, also works in a BigCouch database. And it works, using a similar merging algorithm as the views, except that when it comes to changes, there's not really a global ordering. You don't necessarily know, between shards A and B, which updates happened before the other updates. And so that's something that your application maybe has to be aware of. But if you're using a changes feed in the normal way, or you're using it, the way the CouchDB replicator uses it, it works just fine. One small gotcha is that we've tried to stay, consistent with the CouchDB interface as much as possible. But one of the places where we felt we had to change that a little bit was in the choice of the format for the sequence numbers. CouchDB normally in your changes feed is just giving you, auto increment sequence numbers, right? And that's because it's just got the one database to worry about, and that's a fairly simple thing. But auto increment doesn't make as much sense in a globally distributed system, and we need to encode more information about how to resume that feed, which is what this is really all about. And so we have chosen to just convert those into strings, and I think that's something that we'll talk about with the CouchDB team about whether it makes sense to just always use strings to keep clients simple. I may take a second here and look through the questions that people have been asking before I go further. So I got a question that views are executed on each node, right? How does this affect the limit of scalability if views are executed very often? Well, there's a couple of different ways to approach that question. From the perspective of the indexing performance, you do quite well because you are distributing the workload over a larger number of machines, and so there's less work for each individual node to take care of. But if you're talking about the extra merge sort workload, yes, there is a decent amount of load that needs to be done on the node handling the request in order to do that merge sort. But the next question that was asked, so I just lost the question, but I believe the question was whether merge sort required a lot of extra temporary disk space. And the answer there is no. This is entirely done in memory, and it's done in a streaming fashion so that it doesn't use a lot of extra memory. So it's kind of neat, actually. Each of the workers in the BigCouch database starts sending their portion of the view to the coordinator, and they send it row by row. And the coordinator kind of serves as a traffic cop and says, okay, I've heard from everybody I need to hear from in order to make this determination of what the first row is. And it sends that out to the client, right? And it keeps track, do I have the information I need, which is basically, have I got at least one row from each, shard that I care about? And if it does have that information, it can decide, okay, now I know what the right answer is. Now I know what the next row to send out is. And it just kind of keeps repeating that process. And so the actual merge sort executes in basically constant memory space on the coordinating node. But it does get executed in response to each view request. And so if you have a very heavily sharded database with a very high queue, there is a decent amount of work that needs to be done to compute that view response. So that's true. And that's just the way it works. Is it possible to offload merge sort for view result merging to a different node? You meaning to have a node that only takes care of merge sort view result merging and doesn't actually take care of storing the data? The answer there is, at the moment, not really, but it would be quite straightforward to add that. Actually, no, you could do it. You would have to join a node using distributed Erlang so that it knows how to talk to the other nodes in the cluster, but you would have to keep it out of the actual nodes list, so you wouldn't add it to the nodes database. And if you do that, it'll never store data, but it'll still know how to locate the data that lives on the other nodes, and it'll know how to do the computations and deliver the results to clients. So you could, if you wanted to, have a pool of diskless machines that are actually answering requests from your load balancer and doing all of that work, but aren't actually responsible for storing any of the data themselves. And Dennis asked, what's a high queue? So that really depends on how many nodes you have in the system as well. The queue is just the number of shards in the database. And from my perspective, something around 10 shards per node, right? So if you have 6 nodes, a queue of 64, that's a reasonable thing to do. If you go to 20, 30, 40, 50, it tends to be a lot of active file descriptors and a lot of files that have to be accessed on that one node, which is fine to a point, but you start running into issues with your disk kind of thrashing about because the files are all over the place like that. So I'll just kind of keep moving here since this is kind of the end of one particular section. David again asks, how often is the coordinator hotspot becoming an issue in the field? How do you deal with that? Could I assign subset of my cluster to be coordinator nodes? We don't tend to find it being a huge issue. In terms of the work that the coordinator node needs to do, it's it is the most intensive thing that has to happen in BigCouch. Everything else, is taking advantage of the consistent hashing to make sure that the work is very evenly distributed. But when it comes to downloading a big view response, that work does fall on the one node. But unless you're talking about a very large database and a very high number of concurrent accesses to the same view, it's not the sort of thing that's going to dominate the load on the system. And if you are talking about that, I think my recommendation would probably be to have a caching proxy in front that that to offload some of that work so that the view doesn't need to be fully recomputed every time. And Arnie asks, is it possible to replicate between multiple BigCouch clusters? And the answer should be yes, provided that there's one caveat right now, which is that you should specify the replication request using URLs. BigCouch doesn't quite know how to deal with a locally specified database right now. It just passes that on to the embedded CouchDB layer. But if you tell it, URLs on both sides in your replication request, that should work just fine. And it's something we've taken advantage of to do multi-data center setups at Cloudant. And Fu asks, does BigCouch do full text indexing like React does? Out of the box, no. No. It's something that we've talked about, but I think it's a conversation that needs to happen in the larger CouchDB community too, because many of the full text indexing solutions that we would talk about for BigCouch would be appropriate for CouchDB as well. And Bart asks about any recommendations for multi-data center setups, which are geo-distributed. Well, in that case, I would not recommend running a single BigCouch cluster in which the different nodes are living in different data centers. Erlang doesn't deal with that all that well. It does expect that the latency amongst the nodes is quite, is pretty low, and that interruptions don't happen all that often. So, and I think this is consistent with the recommendations that you get in other distributed Erlang applications too. I think it makes more sense to run a BigCouch in each of the clusters, or in each of the data centers, and replicate in between them. And that's what we've planned on doing. At Cloudant, we have BigCouch clusters on the East Coast and the West Coast, and we replicate between them. Great. So I think I tackled most of the questions there. Yep. So now I'm going to switch gears just a little bit and talk at an even lower level for those of you who might be Erlang hackers or might have browsed the CouchDB code base at one point in time and might be interested to see how this fits in with the rest of CouchDB. And so this slide is not meant to be authoritative here, but the way BigCouch is structured is as a set of Erlang OTP applications that live beside the Couch OTP application in a specific Erlang virtual machine. And I'll talk a little bit more about each of those applications now. So the first one we called Mem3. And so Mem3's only responsibility is to maintain local CouchDB databases that have the information needed to figure out how to distribute a BigCouch clustered database. So there are a couple of these databases. One you saw when we were creating our first BigCouch cluster, and it was responsible for just storing the node list, right? That's all it does. And it just automatically replicates that node list to every other node in the list, right? So I put a node in, and automatically those two nodes agree on each other being a part of the cluster, right? If I delete that document from the database later, that node disappears from the cluster and no new databases are assigned to it. And the second database is the DBs database, which can be, lovely redundant, but it's actually been a really useful thing and a good design of the system. In this local database, which again lives on every machine in the cluster, you've got documents which represent the clustered databases. So they'll have information about how many shards, are comprising that particular database and where those shards live and how many copies there are and where the copies live, as well as just a change log of, shard assignments and, in cases where we've needed to move shards from one machine to another. Maybe we had a node fail, or maybe things grew quickly and we needed to add capacity. It just logs, we moved this shard A from node 1 to node 2. So that's what Mem3 does. The next application really has nothing to do specifically with CouchDB, but it's something that we felt the need to develop in order to make BigCouch performant in a distributed Erlang environment. So BigCouch does a lot of these parallel remote procedure calls to different nodes. You saw this when we were talking about the merging going on for different views, and that's really where it's fairly heavy. And Erlang ships with a nice remote procedure library, but it wasn't really designed for the kind of heavy parallelism we were talking about. And on a very low level, when I had to dig into the code to figure this out, but it spawns processes all over the place. It spawns as many as 3 different processes to deal with one remote procedure call. And when you want to do hundreds of these in parallel, it tends to be a lot of processes spawned that aren't going to live very long, and it's a lot of work. Another thing that happens is that when you take advantage of Erlang's remote procedure library, the responses that you get from the other node, they're actually redirected back through a single process on the remote node, this rex process. So you send the request through that guy, but then the worker that gets spawned off on the remote node also responds back through that same process. And it becomes a bottleneck if you do this often enough. And it also does a little bit more just to be safe, in which it actually forces rex to be monitored so that in the event that the other node's actually down, about it and your remote procedure call fails rather than just hanging. But we saw these limitations, and we saw how they were making the load on our BigCouch machines go up more than we wanted it to. And so we built a new RPC library that you have to be a little careful about using because it removes some of these safeguards that ship with a normal RPC library in Erlang, but the efficiencies that you get if you know what you're doing when you use it are quite significant. And so what we do is we have a setup where there are no middlemen. The process that you submit the request from is the one that's going to get the responses. The workers on the other nodes can respond directly back to you. There's a little tag when they get spawned that says, use this tag in replying back to the original guy. And so it cuts out the middlemen on both sides, really. And if you do want to, monitor the remote process that is responsible for spawning the worker on the other node, which is a safe thing to do. I mean, you never know if a guy is actually dead. You want to know about it. You don't want to just hang and waiting for a response that's never going to arrive. The features that we added for that in what we call Rexy occur out of band. So they don't get in the way. They don't add latency to the actual, determination of the view response. So it's a fairly cool little thing, and at the end of the day, I think it significantly decreases the latencies that we observe in doing views with BigCouch. And it's a purely general purpose thing. You just have to know what you're doing. But you could use it for any distributed Erlang application. It wouldn't have to be couch specific. And then the last two are really where the core, the next one is really where the core of the logic occurs, and that's what we called Fabric, which is a bit of a CouchDB inside joke. It was the original pre-JavaScript query language for CouchDB. And for us, it's now the sort of routing mesh for BigCouch. So it's a library application. There are no processes involved in Fabric. And it's responsible for taking all of the normal update document, open document calls, and replacing them with clustered versions. So it takes care of the write quorum and read quorum logic that I talked about. It takes care of computing when a view is ready to be merged and sent to the client and all of that. And at the same time, I think it provides a fairly clean Erlang interface to BigCouch, and one that I'm hoping we can kind of parallel in the normal CouchDB. It doesn't do any HTTP, but it does everything else at the Erlang clustering layer. And then we just have the last application is basically a cut and paste of what's already in Couch, but using Fabric. So I think we're doing well on time here, and I'll just go ahead and summarize. BigCouch is putting the C back in CouchDB. That's our tagline. We'd love for people to get involved to try out the code. It's on GitHub. It's based off of Apache CouchDB 1.0.1. So it's a straightforward rebase there. You can take a look at the commits and see what all happened. And we put together a brief survey for people who are using BigCouch. We'd love to hear more about how it's working for you, what things are missing, what things you see needing to be added, and that's that third link that you can see right there. So with that, I'll take a step back, and that's the end of my formal talk, and I'm happy to handle Q&A for the remainder of the time that we have. Catherine, did you want to say a word, or should I just jump into the questions? Okay, maybe I'll just go through the questions that have popped up in the rest of the time here. Let me just pull them up. David asks, how does BigCouch deal with a node failure? Does it start automatically reassigning shards to other nodes? And the answer there is no, it doesn't. All it does is note that the node is down. It doesn't try to submit any more requests to it. And then when it comes back up, currently BigCouch doesn't do anything other than just allow requests to hit it again. And if you try to read a document that was updated while the node was down, that inconsistency is detected on read and repaired. One of the things that we've done at Cloudant that we'll be adding to BigCouch is detecting when that node comes back up, triggering a replication automatically from the other shard copies to repopulate everything that was missing in between. And so that's ultimately what we plan to be doing. And I've started work on bringing that into BigCouch. It's just a matter of kind of refactoring a few internal things at Cloudant to make sure that that happens in a clean fashion. Bart asked, any plan to add a binary protocol aside from HTTP? It seems like Fabric is a good place to hook it in. And that's absolutely right. Fabric is absolutely the place to do that if you were interested in something that didn't use HTTP. I don't personally have any near-term plans to do that. And it is something that we've talked about at Cloudant as to whether that's something that people would need to have a native driver kind of thing. But we have no definite plans. The questions come up once or twice on the CouchDB list as well, and it's something that we would want to coordinate there, because at that point you're talking about something that is really, you can do it equally well for CouchDB or this clustered BigCouch version. David asks about the license, and yeah, it's Apache 2 licensed. And Alexander asks, for example, I already have databases A, B, C, and D, each on its own server. Could I set BigCouch on top of them, or must I create a new cluster and merge them into it? You would be better off replicating those databases into a BigCouch cluster. You could, if you wanted to, use BigCouch side by side, I think. It's not something I've tried. It's something I'd be interested in supporting if it doesn't actually work already, would be to install BigCouch, have it continue to serve those undistributed databases from those servers. And then if you wanted them to be BigCouch databases, to just kind of replicate back in onto yourself, and they'll be set up as BigCouch databases. So it's an interesting question. And if it doesn't work, I think it would be straightforward to patch the few things that need to be patched in order to make it work. Phil asks, what about compaction? So my position with BigCouch has been that you don't want to run compaction on all the shards in your distributed database simultaneously. You'd probably want to schedule it and stagger it in such a way so that you kind of mitigate the extra work that's being done, so that you can still respond more quickly with the shards that aren't running compaction at that point in time. So I'd prefer to just keep compaction running locally on the machines. And one of the things that you can do with BigCouch is the regular old unclustered HTTP interface is still available. Futon is still available on everything without the clustering thing. So you can see the individual database shards, and you can poke around in there and say, hey, I want to compact this shard of my database, just by looking at the sort of backdoor interface of BigCouch. And so that's generally what we've recommended at this point. And for our own purposes at Cloudant, we have stuff that does that automatically and monitors the different database shards for when it's appropriate to compact them and triggers jobs off. Nathan asks, is there a monitoring interface that monitors the shards in the cluster? For instance, document BLAs on shard X and Y. what we do have is, the nodes database actually, or the DBs database actually adds nice information about, what shards live where. So you can just browse those JSON documents and write views on that DBs database if you want, so that you can see how many shards are stored on node 1 and how many are on node 2 and so on and so forth. As far as the state of a particular document, there's nothing at this point, but that's probably a good idea to just add a little a little interface that says, like, here's a document ID. Where would you store this? That seems like something that would be simple to add. Daniello asks, are there plans to add chained MapReduce functionality to BigCouch? I don't know how many of these things might have been answered in the chat, but they're sitting in my Q&A, so I'll just give my response to that. We talked about this a little bit on the CouchDB mailing. Chainable MapReduce is something that we have at Cloudant, which allows a view to be persisted as a database, a new database, so that you can run another layer of views on it. And it's really kind of orthogonal to the stuff that we've done in BigCouch. There's nothing inherently, there's nothing that chainable MapReduce needs that exists only in BigCouch. So I think I would prefer to see it, see the design and the basic implementation and everything added to CouchDB, directly. And if everybody agrees that, yeah, that's something that should be added to CouchDB as a native built-in feature, then it's something we would add to BigCouch. But I want to try to avoid making BigCouch too much of a fork from CouchDB right now. I think it's important to say, look, here's a straightforward, set of patches that takes CouchDB and adds all of this. We've already added so much. I don't want to just add other new features necessarily. If it makes sense to just add them to CouchDB and go that way first. David asks if you can set W equals 0. Well, what you can do there is you could set W to 1 and add the batch equals OK flag that CouchDB supports. So in that case, you will get a response back as soon as CouchDB has accepted the document. It's still HTTP. You're still going to wait on a response unless you've written some HTTP client that sends a request and then just ignores everything else on that connection. But that'd be the closest thing you can get. So you could get W equals 1, and you would get a response back before the data had actually been written to disk. You would get a response as soon as the HTTP layer had accepted the request. So that would probably be my recommendation to simulate that. Paul asks for a brief walkthrough of the process of adding new nodes and migrating data off of full ones. Yeah, that's something that we're working on making, more user-friendly than it is. Some of the tools that we have internally aren't quite ready for prime time. They're not ready for public consumption. Adding new nodes on the face of it is very simple. You just follow the same procedure that you did before. But of course, those new nodes won't automatically, at the moment, they're not automatically taking data off the full nodes. New databases will be, the shards from new databases will be stored there, but not the old ones. So as far as migrating data off of the full ones, you're pretty much responsible for getting the data migrated yourself, whether by replicating on using the backend interface. You can replicate one database from one shard to another, and then you can update the DBs database and say, okay, I've moved this shard, right? And so you would edit the DBs database record, and it would say, that shard A used to live on node 1. You would just change node 1 to node 2. And when you update that document in the DBs database, all requests would route to node 2 for that shard. And so that's the basic procedure that you need to do. But of course, it could be done more cleanly for you, and made as atomic as it can be made. But that stuff is not in BigCouch right now, and it's something that we're keen to add as it makes sense. I asked about the changeable MapReduce. Nitin asked about SSL. There should not be any difference between SSL support in CouchDB and in BigCouch. It uses essentially the same libraries. So whatever the SSL support was in CouchDB 1.0.1, which I know wasn't perfect, but it did exist. The replicator had a little bit of trouble with it, I think. That's basically the status of SSL support in BigCouch. Metin asks about using BigCouch and GeoCouch together. I don't think you have a whole lot of options for that at this point in time, but I know that we're both working on making sure that that these sorts of things are interoperable more cleanly. I haven't followed all of the development of the GeoCouch project, my understanding is that there are a couple of details in the storage layer, at least, that are preventing it from being, distributed with CouchDB. But as soon as those are resolved, I think the important thing here is to try to reduce the entropy of the problem here, and to work on individually getting GeoCouch integrated properly with CouchDB, and to get BigCouch integrated with CouchDB, and to kind of use the CouchDB project as the umbrella that would allow them to both work together. I think it's just the way that these things have developed. I mean, they're pretty significant new features that bring a lot of new code, and so you can kind of consider them as feature branches if you like, and they haven't been merged together yet. Another question about whether shards redistribute when you add a node and whether you can remove a node. I think I answered the one about the redistribution. It is manual at this point in time. If you can remove a node, yes, you could remove a node. You would, the shards that were living on that node would be inaccessible, which, if you have the redundant copies, then you'd be okay. But, you would normally want to move that data back onto another live node in the system or a new node and update the partition tables. And again, that's the sort of thing that we have some internal tools to do, but nothing that's been released into the BigCouch code base yet. David asked about moving the BigCouch fork back into the CouchDB code main code line. Yeah, I think it's something that we're absolutely interested in doing. It's going to be a big move, so it's something that is not going to be a part of CouchDB 1.1 or anything like that. But I think it's important to have this thing out there in the wild right now. Make sure it's stable. Make sure it's matures a little bit, and then we can talk about merging it in. Michael asks if I can make a general statement about the performance of BigCouch versus a single CouchDB instance. Will users notice a difference in the performance of the application? Sure. So if, the simplest possible case you can talk about is when you're not even storing redundant copies of the data, right? You're just storing one, and you're just sharding a database, and you've got a bunch of nodes. In that case, you should see, basically linear speedups in the tons of overhead in the BigCouch code base that would slow things down. So we've been quite happy with that so far. Obviously, there's an upper limit to that at some point. You've got so many resources at your disposal that your clients are not going to be able to take advantage of. When it comes to views, that's where things get a little bit hairier because there is a heck of a lot more work involved in coordinating view responses from different nodes instead of just walking a B tree on a single machine. But like I said, we've developed entire OTP applications designed to keep the latency of that operation low. And I think that we've got users who do make extensive user views to serve, live web pages to users, and that, is something that works for them. Benjamin asked, what features, apart from indexed views, set BigCouch apart from other Dynamo-based solutions? I think that the ability to choose on a database-by-database basis what replica levels and sharding levels you're getting is actually something that's kind of cool. I think that the support for that in BigCouch is a little bit better than what you get with some of the other Dynamo-based solutions. Although, I have to, preface that with the fact that I'm far more familiar with BigCouch than I am with Cassandra or Riak or that sort of thing. Yavor asks if it's possible to do rolling upgrades of CouchDB, and it looks like, yeah, Brad and Joe all answered that one. We do that quite often. So, yeah, that works quite nicely. And David asks, yes, if a node goes down, what properties of it do we need to implement on a replacement node, replications, etc.? So normally, if a node goes down and you just want to put a new node back in to replace it and you lost the data or whatever, you put the new node in and you would write a little view that consumes the DB's database and replace the IP. I mean, if the IP is the same, you're fine, you're done. If it's a new IP address, then you need to write a little view that analyzes the DB's database and replaces all instances of node A with node, A.2, right? And then, after some time, read repair would ultimately restore proper redundancy levels. And as I was saying earlier, we're going to do automatic replications of the different database shards together to speed that process along. Great. So I see more questions coming through on the chat window. I know it's 2 o'clock. I'm not sure exactly how these things work, whether it's a hard cutoff or how it goes. But
hey, Adam, I think that we should probably wrap up unless, so possibly you could answer if there are any remaining questions, tackle them on your blog. Would that be possible? Do you have a blog?
Yeah, sure, that'd be great.
Okay.
Yeah, so we
right.
can,
so
if there are questions that we didn't tackle here, we can do blog.cloudant.com and wrap up with the questions that people are adding at the end.
Good, and we can send everyone a link to that when we send out the follow-up webcast. I mean, the follow-up email. Oh, one more question. The question on reaming. Did you catch that one? Let me see if I can find it.
Question on. No, I don't know what that means.
Remaining. Sorry. Okay, there are just 3 or 4 more questions. Can you get the last few?
Sure.
All right, we'll just do them here.
Nikolai asked about supported platforms. We have the most experience running on OS X and Debian flavored Linuxes, and so that's where you're going to find the best support. I think it's something we should, kind of do a concerted effort on to make sure that it's supported all the places that CouchDB works. We've just made no effort to run it on Windows or to run it on FreeBSD or Solaris at this point. That said, there's not a lot of, non-Erlang code involved here, so, it should be a straightforward thing to make sure that it's supported wherever CouchDB is. And whether you can have heterogeneous systems with different operating systems on different nodes in the cluster, absolutely, that would be fine. And Paul asked about suggestions for file systems to use. Well, I haven't used Solaris for BigCouch, and I haven't used that crazy Linux port of ZFS either. ZFS is obviously a very cool file system, but I can't speak from personal experience about its applicability to BigCouch. It seems like it would be a great choice. We actually use XFS a lot at Cloudant. It has good large file support, which is a common thing for us. And I think its failure modes, which can be a little weird for some databases, the failure modes that it has actually work quite well with CouchDB. So, I think I can say we can recommend it. You should talk to Joe Williams on Twitter if you want, more detailed infrastructure recommendations as far as that goes. And I think that's about it. Oh, and ETA on making the functionality and tools for auto redistribution and balancing of the sharded data. Bart, I think that probably is about a month out, tentatively. Like I said, it's the sort of thing that we've got internal tools for. Bill, I don't know enough about GlusterFS. I only know a little bit about reading the overviews of it, but I don't think that would actually be. I'm not sure that would be an appropriate choice. I think it's more of a clustered file system, right? Like a Hadoop file system or something like that. But I could be totally wrong about. Anyway, thanks so much for your time. I really enjoyed speaking to you guys about this project that we've been working on for years now, and we're really happy with. So, yes, thanks again, and thanks to O'Reilly for putting this on.
Thank you, Adam, and thanks to everyone else who joined us for this. Great webcast. It's a little over my head, but I really enjoyed it. And I could tell other people did too. So we will have a recording of this available shortly. As I said, it'll probably be early next week, and we'll send everyone a link with that as soon as it's ready. And you'll all get that. And I hope you can join us again. We're going to have another CouchDB webcast in November. We haven't set the exact date yet, but we'll probably have a link to that also to register in the recording available email that we send on Monday or Tuesday. So thank you, everyone. I hope you'll join us again. And thanks, Adam. Great job. Bye.